Welcome to DWBIADDA channel. Please subscribe for latest training videos.
Hi, in the last session we learned about how a simple linear regression works. We had a scatter plot with the dependent and the independent variables, and the objective of the linear regression is to draw a straight line through these data points. Let's try to implement that. Let's try to draw two straight lines. One would be y equal to 10 plus 12x. Other will be y equal to 6 plus 18x. And let's see how these two straight lines perform. So apart from this, let's say we do not have any idea about a linear regression. In such case, given the data set of the units and the minutes, if somebody asks what would be the number of minutes a person would take to fix a certain number of computers, our first intuition will be to have the average. We would consider the number of minutes to take in to fix a computer is uniform throughout, and that is the average. That would probably be the worst prediction model we can think of. So let's try to have all the three together and try to compare each of them. So I make the first model, which is nothing but the mean of the minutes. Second model, I make it as 10 plus 12 into computers.units, which is nothing but the x value. Second model is 6 plus 18 into computers.units. I add a column to the data frame computers with the values of all the three models. Let's try to have a scatter plot for all the three models. The first, I do a scatter plot of the normal variables of the data sets, and I draw three lines on this scatter plot, each for the predictions which I made right now. If we see here, the red line gives me the prediction for the mean, which is a straight line. This is self-explanatory. Because it's a constant, so it will be a straight line. Now let's look at the green and the black. The green line is for the first model and the black line is for the second model. If you see here, the black line goes slightly above the points of the data sets. The green line goes slightly below the points of the data sets. So we can say one of them is the best possible prediction, but these are not the only two lines which are possible. I can actually draw n number of lines through these points with a slight inclination. So now the question is, which line should be considered as the best line and should be the line for my linear regression? To answer this question, I would like to introduce two terms. One is a residuals and the other one is the R-squares. Let's try to understand what is a residual. Residual is nothing but the error that we commit while making a prediction. For example, in the given plot over here, the line is our prediction and the blue dots are the actual values. So let's consider for x is equal to 2. My prediction is 4, but the actual value is 7. So I have made an error of 7 minus 4. Similarly, I can calculate the error for each data points. If we note here, there would be some negative values, there would be some positive values as well. So now we have something called ordinary least square methods. As a part of that, in order to avoid the discrepancy caused due to the positive and the negative values, we square the errors that we commit in our prediction and add them all. This value is called the residual sum of squares, which means the square of the errors for each data points that we commit after we make our prediction. So RSS is nothing but e1 square plus e2 square up to en square. N is equal to the number of data points which we have in our data set. We'll replace E1 by the equation of y equal to beta naught 0 beta naught plus beta 1 x. So E1 is nothing but yi minus y pred. Yi is the actual value, y pred is my predicted value. And I can replace y pred with my equation of the straight line. So RSS can be rewritten as y1 minus beta naught minus beta 1 x1 whole square plus y0 minus beta naught minus beta 1 x2 whole square. It goes on till yn. In other words, it's a summation of yi equal to 1 to n being the number of data set, yi minus beta naught minus beta 1 xi whole square. This is the equation that I can write for my RSS. Now, which will be the best fit line? The best fit line is the one which has the minimal value of RSS. In other words, which has the minimum errors. How do we count that? To have the minimum value of RSS, either I can do a differentiation based on the base x, or I can use another method which is called gradient descent. Gradient descent is nothing but an iterative method. It keeps on checking for each iteration and it has a learning rate. Based on the learning rate and the iteration, it tries to predict the value which has the least value of RSS, which is nothing but the residual sum of squares. We'll learn about gradient descent in detail in our subsequent lessons. So that was about residuals. I will introduce one more terminology called R square, or the coefficient of determination. R square is nothing but 1 minus RSS by TSS. When I say TSS is nothing but the sum of the square of errors from the mean. Just like we calculated the residuals as the sum of the squares from the predicted value to the actual value, TSS, which is total sum of squares, is the difference of the predicted value from the mean of the value and square it up. It turns out that R square always lies in between 0 and 1, 1 being the highest and 0 being the lowest. The higher the value of R square, the better my model is. If we look at these three pictures over here, this is the picture which has an excellent fit. I can say by looking at this picture, there is a minimal error. The distance between the predicted value and the actual value is the minimum. And I see here the R square value is 0.9. I reduce the R square a little bit and I see there is a variance. I see the noise starts increasing and the distance between the predicted value and the actual value starts increasing. I increase the R square a little bit and it becomes a bad fit. If you see here, the distance between the points and the straight line which I draw seems to be quite high as compared to the other two. This gives me a holistic picture of what R square is. In other words, the higher the R square, the better my model is. The lower the R square, it's not such a good model. Now, this is the concept which we will be using in our linear regression model going forward. In the next lesson, we would like to use the same concept of R square and the RSS to compute the best fit line using the different modules and the different packages available in Python for the machine learning. Thank you so much.